Let's continue our journey into simplifying and combining radical expressions. But in this video, I want to mix in some examples where we have to simplify radical expressions that contain variables. And you'll see that we have to treat these a little bit differently than the examples that we've done previously, where we only simplify and combine radical expressions that contain numerical values. So when we have to simplify and combine radical expressions that contain variables, we'll treat them just a little bit differently. So here we're asked to add the radical expressions. 2 times the cube root of t to the fifth plus 2t times the cube root of t squared. Notice that these are not like radical terms. The first term is the cube root of t to the fifth, and the second term is the cube root of t squared. But let's simplify each of these radical expressions to see if we do in fact have like radicals that we can combine. The largest perfect cube that will evenly divide t to the fifth is t to the third. So we'll rewrite t to the fifth as t to the third times t squared. That gives us 2 times the cube root of t to the third times t squared. The radical expression, the cube root of t squared, is already fully simplified because there's not a perfect cube variable expression that will evenly divide t squared. So our second term, 2t times the cube root of t squared, is already fully simplified. Now let's continue simplifying the first term. The cube root of t to the third times t squared is the same thing as the cube root of t to the third times the cube root of t squared. And we'll continue bringing down our second term because it's already fully simplified. Back in the first term, the cube root of t to the third is t. So our first term is 2 times t times the cube root of t squared. We can't simplify the cube root of t squared because it's already fully simplified. And we continue bringing down our second term. And at this point we notice that we have like radical expressions. The first term is the cube root of t squared, and the second term is the cube root of t squared. And here's where the difference comes in. It's important that we notice on the outside of our radicals that we have like terms. 2t and 2t are like algebraic terms. If these two terms were not like terms on the outside, we wouldn't be able to combine these cube root of t squared terms. And here's why. Look at this expression over here on the right, 2x plus 3y. I can't combine these two terms because they're not like terms. One of them is an x term and the other is a y term. And we know that algebraically we can't combine algebraic terms that are not like. So 2x plus 3y wouldn't simplify and we wouldn't be able to combine those two terms together. The same idea goes into play when we're combining radical expressions like the ones we see here. I can only combine t terms with other t terms. So here we have 2t cube roots of t squared plus 2 more t cube roots of t squared. And the question is, how many total cube roots of t squareds do we have? 2t plus 2t is 4t. And again, we're only able to combine those outside expressions because they are like algebraic terms. So that gives us a total of 4t cube roots of t squared. So just to reiterate my point further, if we have an expression like x square roots of 2 plus 3 square roots of 2, we notice that we do have like radicals because we're adding a square root of 2 to a square root of 2. However, the expressions on the outside of the square root symbols, here an x and a 3, they are not like terms. So we can't combine these radical expressions because we don't have like terms on the outside of the radical. The best that we can hope to do in this situation is factor a square root of 2 from each of these terms. If we factor a square root of 2 from the first term, x square roots of 2, we have x remaining. And if we factor a square root of 2 from the second term, 3 square roots of 2, we have 3 remaining. So if we factor a square root of 2 from each of these terms, we'll have the square root of 2 times the sum x plus 3. In this situation, this would be considered a correct answer, and that would be considered the correct answer. One is just written in factored form, and the other's not. Let's do one more example. Here we're asked to add the radical expressions. And we have the expression 3s squared times the cube root of st to the 6th plus 7t squared times the cube root of 8s to the 7th. These are not like radicals because the first one is a cube root of st to the 6th and the second one is the cube root of 8s to the 7th. But let's make sure that both of these radicals are fully simplified. We could rewrite the first expression as 3s squared times the cube root of s times the cube root of t to the 6th. And we can rewrite the second expression as 7t squared times the cube root of 8 times the cube root of s to the 6th times the cube root of s. Continuing to simplify, the first expression gives us 3s squared times the cube root of s times the cube root of t to the 6th. But the cube root of t to the 6th is t squared. In the second term, we would have 7t squared times the cube root of 8, which is 2, times the cube root of s to the 6th, which is s squared, times the cube root of s, which is already fully simplified, so it stays the cube root of s. Continue simplifying. In the first term, 3s squared times the cube root of s times t squared can be rewritten as 3s squared t squared times the cube root of s. And the second term can be rewritten as 7t squared times 2, which is 14t squared, multiplied by s squared. That gives us 14t squared s squared, or 14s squared t squared, and that's still multiplied by the cube root of s. Now that we've fully simplified both terms, we notice that the first term and the second term are both cube root of s terms. However, because we have algebraic expressions on the outside of our cube root and not just plain old numbers, we have to make sure that we have like terms on the outside of the radical as well. Notice that the first term are s squared t squareds on the outside, and the second term are s squared t squareds on the outside. So we do have like terms on the outside of our radicals. So because we have like radicals and like terms on the outside of the radicals, we can combine these two radical expressions. And we know that once we combine these two expressions, we're going to have s squared t squareds times the cube root of s expressions. The question is, how many of those things do we have? In the first term, we have 3 of those things. And in the second term, we have 14 of those things. So altogether, we have 3 plus 14 of those things, which gives us 17. So we have 17 s squared t squared cube roots of s things.